Okay, so heat treatment of steel. Why are we going to heat treat steel? And by the way, a lot of different materials are heat treatable. Aluminum's heat treatable. In fact, most of the time you find it in the heat treated condition. Okay, but for steel, it's particularly you can vary the steel's performance by how you heat treat it. If you want something hard, you're going to lose a little bit of ductility. But if you want something really hard, so you're going to cut something else, then you can do that by some sorts of heat treatment if it's the right kind of steel. So what we're going to teach you about is and this is going to be helpful in your analysis, is that, well, what kind of steel would I want? What makes it harder? What makes it tougher? What alloys are good in the steel, and all that kind of stuff. Okay, so we're going to try to get you there as quickly as possible here. Again, this is just a brief overview. The books that you see behind me, all those red books and all these other red books down here, those are all on metallurgy. So I'm not going to teach you all that knowledge in the next, 30 minutes or so. By the way, I have 60% battery and I don't have my charger. So if I just disappear at some point, well, we're done for the day because that's all the battery I have. Okay, so we want to produce more machinable, tougher, higher strength, harder, formable steel. We got to have the right steel for the application. What's the deal here? Okay. So one thing we haven't talked much about yet, we've talked a little bit about those properties, but we haven't really talked about why the properties change. And there's kind of stuff going on at different levels. Like when I say levels, I mean like size levels. Hold on, Henry's on the phone here. I'm going to pause the, okay. Okay, so at different size levels, you're going to have different things going on. So at the atomic level, and this is what I want you to kind of be able to imagine stuff happening at the atomic level, atoms rearranging and what's going on actually. So we're first going to talk a little bit about crystal structures and that kind of thing. Then we're going to talk about microstructure, which is the crystal structure is how, and don't forget this because this is going to be in your report. The crystal structure is how the atoms are actually stacked. Now, if you think about atoms as like little balls, you can actually stack balls differently in order to get different atomic arrangements, believe it or not. They have different densities. They behave differently. So you would think that little spheres, you can only stack them one way, but you can actually stack them a bunch of different ways in order to get these different crystal structures, okay? And there's a whole bunch of them, but there's generally three that we deal with metals. Generally. Okay, so the microstructure is groups of those atoms. So it could be, well, we have clusters of certain atoms over here and clusters of other atoms over there. And then when we look at it under the microscope, we see a difference in those arrangements. We've actually seen these a little bit when we talked about cast irons. We saw some microstructures, okay? So think about it this way. Crystal structures is the actual crystals, the little bitty crystals that the atoms are made out of. You can't see them with your naked eye. Microstructures is what we can see under the microscope. And it says something about, it's predicted from the iron carbon phase diagram. What is that? Okay, the iron carbon phase diagram. Let me change slides here. Okay, we'll get to that in a minute. But the iron carbon phase diagram, as far as I know, and as far as you're going to know, is the most important diagram ever known to mankind, literally. Okay, so I'm going to back that up in a little while. So the crystal structure here is a body center cubic. So you think about four atoms sitting on a flat plane. We put one atom on top, and then we put four more on top of that, and that structure would go on kind of like indefinitely. Okay, and these are atoms, so they're really small. When you stack the atoms this way, the interstitial spaces, the space between the atoms, remember that there's atoms are round. So when three atoms are next to each other, there's a little hole in between them. That's called an interstitial space. Those are really small in these. So it would take a really small atom to be able to fit in between those atoms, okay? So generally there's two types of alloys. There's substitutional, which means let's say if this was iron atoms and you got a copper one in there, and the copper one, because it's about the same size as an iron one, kind of sits just in one of those spaces. But the atoms are different size slightly. So the closer they are in shape, the more likely you're going to have a substitutional type of crystal, atom like alloy. If the atom's really, really small, like a carbon atom, or even like oxygen or nitrogen or something like that, it might fit in between the spaces of the atoms, and that's called an interstitial alloy. Okay. So, but generally, with the body center cubic structure, you don't have big spaces, so carbon atoms cannot fit in those little interstitial spaces. Okay. Weird thing about steel, and this is one of the reasons why it's so prevalent and why it's, still the most important material used today, is that when you heat it up above around 1330 degrees Fahrenheit, we start converting this body center cubic structure to a different structure. And what's good about that is that that other structure is more deformable. That's why we heat metal to red hot, to be able to forge it. You guys did that this semester, right? When it cooled down, you could hardly move it around. When you got below glowing, which is 1330 or so, you couldn't move it very well, okay? You would cold work it, but it doesn't move very much. But when you heat it to a high temperature, you could pretty much indefinitely move that stuff around. So, but at room temperature up to 1333, we get this structure called body center cubic. We also call it alpha iron, and we call it ferrite. A lot of different names for it, okay? It's magnetic, and again, it has the small little spaces for carbon atoms. So that'll be important later on here. Okay. So face center cubic. So when iron gets to 1333, it actually changes crystal structure. This is called an allotropic change. Okay. So an allotropic change is when it goes from one crystal structure to another one without just by going through a temperature change. Okay. So the atoms literally rearrange. And what happens is, it's kind of neat. You can see this. If you take a wire and you heat it up, what happens is the wire will bounce when it gets to that. It actually gets longer because it's, getting hotter. And then it bounces when it gets to like 1333, because the crystal structure all of a sudden changes over to this other structure, which has a different density. You didn't even know this stuff was going on when you were forging, did you? So this is called gamma iron. It's non-magnetic. I don't know if you knew that. Red hot steel is non-magnetic, whereas, in fact, blacksmiths that don't have a furnace that have temperature gauges on them usually will use a magnet to tell when it's non-magnetic, that's the right temperature. You should go and heat treat the thing, okay? So the cool thing is it has larger space for carbon atoms. So when it can hold up to 2% carbon in solution. So here's something that's going to be hard for you guys to understand. If I take carbon and just pack it around the outside of steel, and I put it into a furnace and I heat it up to 1800 degrees or something like that, that's way above when it changes to this crystal structure, right? So what's going to happen? Well, the crystal structure is going to change over eventually when the whole thing gets up to that temperature. So you let it sit there for a while. And then the carbon will start to dissolve. Solid carbon will start to dissolve into that crystal structure, literally. And it's called diffusion. So it actually is like a sponge. It's soaking up, because it can go in between the atoms. It can actually soak up that carbon. It takes a long time. If you ever heard of something called case hardened, where the outside of a part is hardened, the inside isn't, that's how they do it. They actually literally pack, that's one of the ways you can pack your piece of steel in charcoal and put it in a furnace and heat it up to high temperatures in a little metal box or something. And then there's a little bit of a chemical reaction that happens at the surface with carbon monoxide, but essentially the carbon dissolves into the surface, okay? So it can hold up to 2% carbon. And so the thing that's hard for you guys to understand is that a solid can act just like a liquid, in that you could put sugar in water and it will dissolve in the water, right? You can put carbon on solid carbon on solid iron in a little box to contain it, to create, there's a gaseous phase in between, but essentially the carbon migrates from the carbon, charcoal or whatever, into the steel. So it's dissolving carbon in it. When you guys put your screwdriver in the furnace for 15 or 20 minutes or whatever I guess I told you 20 minutes for your screwdriver, what you were doing is, and you didn't know this, you were dissolving carbon into solution. So the thing got up to red hot, and then it created this crystal structure. Then carbon atoms, which were trapped in a different arrangement, then dissolved and became into this structure. So you were dissolving it even though you couldn't see that happening because it's a solid. So I just want to get that in your brain that there are chemical reactions that occur in solids that you can't see. And that's why metallurgy was like a magic back in the old days. It still is magic, but because these things were happening with no visible change in the metal, except for the fact that now it's hard or it's soft, or, you know, we did different. So they actually, in some cases, they actually used rituals or religious rituals to kind of record exactly what you're supposed to do in order to get the right result. Okay.
So the higher carbon content, the tougher it will be, correct?
Sorry, one second here. I wasn't hearing you quite. Go ahead again.
So the more carbon content, the harder the metal will be?
The harder it will be, but there's a trade-off usually. The trade-off is you trade hardness for toughness. So if you ever watch the Forge and Fire show, they hit things and they cut things, right? Those are two opposite. One of them, you want to be hard. The other one, you want to be tough. Ideally, you'd make a structure that is both hard and tough. But typically, once in a while it works, but typically it's a trade-off. So as I go down in hardness, I'm going to go up in toughness, okay? And if you ever watch that show, what they don't show you is that there's a tempering operation. They show them quenching it where all the fire is really cool. Then they take a break for lunch, and they go out and they throw them in the tempering furnaces. Ben Abbott was telling me, like, why don't they ever show that on the things? It's boring. You know, so for the show, they just don't show that part of it. So if you watch at least one episode sometime, and it's pseudoscience, let's call it, but it's interesting anyway. Okay, so what's going on here is this is your body center. You got 4 atoms, one on top. In those carbon atoms, you can see, well, that's the size of the atom that would fit in there. And the carbon atom, is more like this size. Okay, so it doesn't fit in there. So the deal is, think about this. Above 1330, or, you know, as you start going higher above, the carbon can fit and it can dissolve. But when you get below that temperature, it says, get the hell out of here, carbon. I can't handle you in my structure anymore because I got to change back to body center cubic. Okay, so the solubility at room temperature is nearly 0. The solubility at a high temperature is 2%. It varies a little bit with temperature. Okay, so it's kind of like sugar and water. You heat it up, you dissolve a lot of sugar in the water, and then you cool it down, and you have a super saturated solution. Doesn't want to be there, right? Okay, this is even more like that. It doesn't want to be there. In fact, it can't be there, sort of. And we're going to tell you more about that in a second. Okay, so carbon can either be dissolved, or when it can't be dissolved, and body center cubic iron gives it the boot, where does it go? It has to go somewhere. Well, what it does is it says, like, okay, I can't be in solution, but I can create a compound. Now, this is ionically bonded. This is not metal anymore. So when we have 3 iron atoms and 1 carbon atom combining to form a really brittle and hard particle, it's called cementite. So what happens is when you slowly cool the austenite to form gamma iron, carbon can't fit in the interstitial spaces, therefore it combines to form a compound. And that compound, weirdly enough, instead of it just making blobs everywhere, it likes to form in these plates. And if you ask me why it forms in those plates, because somehow it lowers its energy to do that. It's because in Mother Nature doesn't do anything unless it somehow is easier to do it. Mother Nature's lazy, okay? So here we have pure iron. Remember, ferrite is alpha iron, which is just body center cubic iron with almost no carbon in it, right? 0.008% or something like that, okay? And then it kicked it out into the area next to it. It's kind of like threw it in the gutter, right? And so that carbon says, well, I got to do something. And it grabs onto a couple of iron or 3 iron atoms, and it makes this little, but it makes a plate. Now, this is not like, you can't see this with your naked eye. You have to look at this under a microscope. But if you slowly cool the metal, this is what it does, okay? So if we annealed it, remember that you're going to do, in your assignment, we did a bunch of different cooling rates. So you're going to have to start thinking about now, well, okay, that when we did a really slow cooling rate, this is what we got, probably something like this structure that I'm showing you right now. Okay. So these alternating layers of ferrite and cementite are called something. And what are they called? They're called perlite. Why are they called perlite? If you know anything about diffraction, if you in your physics class, remember you have like a lot of little slits, and then if the light goes through the little slits, it creates like a rainbow or whatever, diffracts the light. Okay. So the same thing happens if you take and you polish a sample of this metal, it'll look absolutely shiny. You won't see anything. But if you take some acid and you put it on the surface, like nitric acid, just a very small concentration of nitric acid, what it does is it eats away the cementite a little bit. So now we have dark spaces where those little lines are. And that little grading, the lines are evenly spaced, will actually diffract light. And it looks like mother of pearl, like on the inside of an oyster shell or something like that. So that's why I call it perlite anyway. But perlite is, think about it this way. Perlite is a naturally occurring composite, right, of layers of cementite and ferrite. Now, ferrite is very soft. Cementite is really hard and brittle. So when we make a composite, what normally happens with the composite? Anyone know? What kind of properties do you normally get with a composite? Anyone take a composites class or any classes in plastics there? Well, think about fiberglass. You put a soft resin. The plastic that they use is like really not very strong at all. Epoxy is not very strong. But then you add that to fiberglass. The fiberglass is stronger than steel. It's got like a tensile strength of like 200,000 pounds per square inch or 180,000 pounds per square inch. So really high strength. The problem is it's pretty brittle. So we got a gooey plasticky thing and a brittle hard thing, and we mix the two things together and it improves the properties of both. Okay. The glass isn't quite as brittle and the gooey plastic is not quite as soft and it's stronger. Okay. So having these alternate layers of cementite and ferrite makes it somewhere in the middle as far as the properties go. And this is what it looks like under the microscope. And you can see that it's not all like one row of these things, because what happens is we talked about the crystal structure a little bit ago. So what happens is those crystal structures start to form in the liquid. And then one might form here and one might form there and one might form over here. It's like slush. If you think about slush, there's little particles of ice that have water around them, right? It's exactly the same thing. In steel at 3,000 degrees or something like that, as it starts to cool, little like solid particles start to form with liquid around them, okay? And those grow, and eventually they grow into each other. But the thing is, those crystals are oriented at slightly different angles, right? So now there's a boundary between, you can see right here, there's a boundary between this crystal here and this crystal over here. Okay, that's called a grain boundary. A grain is a crystal. Now, how big are those? Well, this might be under, let's say, 500 times magnification. So they're pretty small. And by the way, they vary greatly in size. You can have them relatively large or you can have relatively small. But if you know anything about toughness, you want to have a lot of these little crystals of random orientation to get a better mechanical properties like toughness, okay? So, how are we doing time-wise? Okay. So perlite looks like this on the microscope. So the white stuff, again, is ferrite and soft. The dark stuff is cementite. The reason why it looks dark is because the acid etches it and the light goes down into those grooves and doesn't come back out as easily, okay? So we have a special microscope. Instead of looking through it, in fact, the microscope's sitting right behind me over here. It's under that cover. But instead of the light focusing through it, it actually reflects off the reflective surface of it. And the eyepiece that you have has like a two-way mirror on it. So the light comes down, shines on the piece, comes up, and then reflects at your eyes, okay? So you need a really bright light. In the olden days when I went to school, We used a carbon arc for the light source because they didn't have light bulbs like LEDs and stuff like they have nowadays. It had to be really bright. Okay, here's something that you want to write down. And just like, this has got to be something that if I ask this question, it comes to you naturally. This structure has an average composition of 0.8% carbon. Okay. So when I say average, what is the carbon content of the ferrite? Well, it has like 0.008% carbon in it, right? Almost nothing. You might as well say zero. So the alpha iron has almost no carbon. The area right next to it has 6.67% carbon. This is by weight, okay? Not by volume, but by weight. So 6.67% by weight. That's something like, well, 25% by moles. Because think about it, if it's Fe3C, right? There's 3 iron atoms and 1 carbon atom. So it's 25% by the number of atoms, okay? But it's 6% by weight. Why? Because carbon is a lot lighter than by weight. Carbon has a much lower density than iron, okay? I know that's a little confusing maybe, but if you took your chemistry class, we're talking about moles, okay? There'd be like, 3 moles of iron atoms for every mole of carbon atoms, average in this structure, right? Because it's not uniform. But if I take and I melt this down, it'll be 0.8% carbon, okay? Perlite is formed during slow cooling. In fact, the slower you cool it, the wider these little plates are. So they're farther spaced apart. Why? Because carbon can migrate farther, okay? Anyone have any questions? Go ahead and ask away here while you think of them. Are we good here? Does you understand what it is? Okay. So since I'm getting lost, I need a map. How do we know what's going to happen? And I said, this is the most important diagram ever known to man. It's called the iron carbon phase diagram, or sometimes they call it the iron carbide phase diagram. Same thing. But it tells us what microstructures are stable at different temperatures, things like ferrite and cementite, and carbon is along the x-axis, temperature is along the y-axis, okay? So here's what it looks like. It looks very complicated. By the way, it probably took about 10,000 experiments in order to develop this accurately, okay? Because and it's really hard to do because I can't look at 2,000 degrees Fahrenheit and 0.8% carbon. I cannot look at that under the microscope to determine what the microstructure is, right? Because it's going to melt the microscope. So what they have to do is they actually quench it from high temperatures, and then they have to try to figure out, well, what was it at that high? It's really pretty tricky to do this, to form one of these diagrams. But this is one of the ones that's been around the longest and probably the most researched in the history of humankind, okay? These regions are sort of like regions on a map, okay? Like if this was Austria, because austenite sounds like Austria, okay? And over here we have, I don't know, depends on what year we're in, but let me see. Let's say this is Germany over here. Well, actually, here's the funny thing. Look at here. Let's say this one up here is liquid. Okay. I don't know what's north of us. That's okay. This is Germany here. This is Austria. What's in between? Let's call it a demilitarized zone. This is back in like World War I or something like that. So we have a demilitarized zone right in between them. It's kind of like no man's land here. And what it is, it's a mixture of the two things. And you always have that in phase diagrams. You have one thing and another thing. I'm not going to say always. You usually have this. And then in between it, you have a mixture of the two. Okay. So it doesn't usually go directly from one to the other. It kind of goes through this region where it's got a mixture of them. Okay. So how do you read this thing? If I have a 0.8% carbon steel and I heat it up to 3,200 degrees, I'm going to have liquid. So you know what phase it's going to be, right? If I cool it down to right here, this temperature here was at 2,700 or something like that. it is just going to start to form solid. So because solid is this austenite stuff, so we have liquid plus austenite. So we're just going to have little crystals of austenite are forming. Okay. And by the way, the names of all these things are actually, it's named after famous metallurgists. Most of it is cementite, not. But and we'll talk about other structures that are named after famous metallurgists. Okay, there's no Metzloffite yet. So liquid goes to liquid plus solid, and then if we keep cooling, it eventually becomes 100% solid. Okay, so this is kind of like slush in here, and then right here, it's solid, right? It's hot, but it's still solid. And then we keep cooling, and then you see there's this one point here. This is an important point here. It goes from austenite to two other things. And this is really confusing. And I'm not going to go too much into detail right now because I'm going to confuse you. But don't look down here. Look up here. We have ferrite and cementite. Way over here in this little bitty region here, Albania, or I don't know, Liechtenstein or something like that. This is alpha iron. Okay. Way over here is a country that's so thin, it's a line. Okay. Why? Because it only happens at 25% carbon, right? Which is 6.67% exactly at that composition, right? That's a compound. So cementite is that compound that happens, Fe3C. And then over here we have alpha. So we would know that we have this iron carbide and we have iron, right? Perlite, essentially. Okay. So I'm going to go on from here. Oh, by the way, if you're making cast irons, you're going to be over. And this is steel ends somewhere in this 1.5 to 2%. Depends on which book you read. Our book says 1.5%. So essentially, I made a cast iron that's actually 1% carbon, but that's a whole another story for another day. But anyway, somewhere over here is the limit for steels. Everything to the right of it's cast iron. Also, cast irons tend to have silicon in them. So this diagram is no longer 2 elements, it's 3 elements. So what does that do to this diagram? It makes it way more complicated. What happens is it actually makes it 3-dimensional. And so you'd have to use SolidWorks or something. And then like, okay, well, I'm cooling down and I'm going to, it does all these weird things because their surface is not, they're not any longer like a 2D diagram. So what we end up doing is slicing that in 2D so you can represent it on a 2D surface. What happens if we have 4 elements? Well, then your brain explodes because your brain does not have the ability to do 4-dimensional math in it, okay? But you can represent it mathematically, just so you know. There's a lot of research that's done on this with, oh crap. So unfortunately, guys, sorry, some of my symbols have like screwed up here. So maybe you can take some notes on this slide that the eutectoid reaction is austenite, and we can, this is the eutectic. See that little point right there? I said it's kind of an important point. This little thing right here. Oh, why do we call it eutectoid? I have no idea. They came up with that word a long time ago. It's kind of like being a lawyer. Why do lawyers have terminology? Because then you have to pay them because you don't understand what the hell they're talking about. Okay. So metallurgists are the same way. It's job security when you don't know what the word eutectoid is. I shouldn't even teach yet. Okay. But anyway, so the deal is that it goes from right here, we go from austenite at 0.8%. Remember, that's a number that I told you to remember. At 0.8% and at 1333 degrees Fahrenheit, it goes from austenite directly to ferrite and cementite. Okay, even it talks about perlite here. Ignore that for a couple seconds because remember, perlite is made up of those alternating layers of ferrite and cementite. So it's saying the same thing, but it's a little confusing right now. So what I want you to just remember now is that up here at the top, the eutectoid reaction is gamma or austenite goes to alpha and Fe3C. And if you think about it, gamma is like a fish swimming downwards. Alpha, I didn't use the right symbol. This is like different version of it, but it's a fish swimming horizontally. Okay, that's how I remember it. Okay, and if you're in a fraternity, they make you remember all that crap anyway. They should. That's what they made me do. Below that carbon content. Okay, so essentially at 0.8% carbon, you have 100% perlite because that's the eutectoid reaction. Okay, this is where it's going to get a little confusing. And I really want you to ask questions if you're confused, because it's an on or an off switch. Either you understand it or you don't, okay? Hypoeutectoid, what does that mean? Holy crap. Another word that, okay. So hypo versus hyper, what do those two words mean? Hyperactive, you may have been called that as a child, okay? Hyperactive means more than active, okay? Hypoactive would mean less than active. So right now, listening to me, some of you might be hypoactive, okay? You're falling asleep or something. So hypoeutectoid, all that means is it's a fancy word for saying below 0.8%, at least in this case. But it's that little V where the diagram comes down. There are eutectoid reactions in other metals, other different phase diagrams. But a hypoeutectoid for iron happens at 0.8% carbon, okay? What happens is, it's like a little kid getting candy. I'm going to try to make an analogy here, or me. So when I get candy, I eat it all right away. I don't save any for later. I just eat it all. Okay. So I'm not allowed, my wife doesn't buy candy because I'll just eat it all. Iron is like that when it's cooling, iron is like that with carbon, making perlite. So what it does is it makes perlite, which, remember, what's the average composition of perlite? 0.8%. So it takes all the carbon it has and makes perlite out of it. Then it's, I don't have anything left. And it's all ferrite left over, okay? So when you look at the microstructure, you'll see, okay, so if it has 20, we'll do this in a second, but essentially you're going to see areas where there's perlite and then areas that are nothing. It's just ferrite. The reason is it used up all of its carbon to make perlite at 0.8% average composition, and then it didn't have anything left over, okay? So hypoeutectoid means below 0.8, which means we're going to have less than 100% perlite, because 0.8 carbon, forms 100% of the structure, is going to be that composite called perlite. This is what hypoeutectoid steel looks like. Here are the areas that it ate all the candy, or the carbon was all sucked up and formed perlite, okay? So, and remember that these things are called grains again. These are just crystals that formed in liquid and eventually ran into each other. And they have slightly different orientations in their crystal structure. So these are called grains. See the grain boundaries, they call it? So that's a grain boundary. For some reason, there's a little bit of a, let's say, a mismatch at those atoms, at those boundaries. And when you hit it with acid, those also etch a little bit too. Okay, so you should be able to see the grain boundaries and the carbides. Depending on what acid you'll put on there, you'll get different pictures. It's kind of neat. So we can develop different pictures, like old-fashioned photography, but I can see different things in there. Okay. Okay, so here is 0.2% carbon steel. This is the stuff that you guys were welding on. This is the stuff that the electrodes were made out of that you're welding with. Okay, so if you would have polished an electrode and looked at it under a microscope, and you etched it with some acid, the dark areas are perlite. We're at a magnification here, maybe 100x, where the little lines are not visible. It just looks dark because they're so close together, okay? If we were to go to 1,000 magnification, then you'd see them. Okay, so what we have here is these dark areas are alpha and carbide, or perlite, right? And this is 25% dark. Now, why is that? Because 0.2 is a quarter of 0.8. So you would expect to see a quarter of the cross-sectional area to be dark, because it roughly equates. This is a three-dimensional thing, right? But if we take a slice through it, you get kind of a slice through that 3D structure that represents the 2D areas then will represent what's happening in the 3D structure, unless something's non-uniform. It's usually relatively uniform. Okay, 0.4% carbon. You can see that we got a lot less light and a lot more dark, okay? So it's 50% perlite and 50% ferrite. This is a medium carbon steel. And again, this is slow cooled. We get something completely different once you get above 0.3%. A medium carbon steel is hardenable typically. So once we get, if we're not cooling slowly anymore, then weird stuff happens, okay? There's a bot. There you go. Okay. I forgot to tell you something. This diagram here, the most important diagram known to man, it has one Achilles heel. It only happens when we slow cool things. So this diagram tells you what should happen or what wants to happen. It doesn't tell you what actually happens always, because if you cool in a non-equilibrium fashion, this won't happen, okay? Sometimes it will, sometimes it won't, okay? So keep that in mind. We have some other diagrams that show you, well, what happens in those other situations. That's why there's that many books behind me, okay? It sounds complicated, but eventually you can start to visualize what's happening in the metal and kind of pretend your brain can kind of like imagine atoms moving around and stuff like that. Okay, so here is exactly that. We're going to try to imagine what's going on according to the phase diagram here. And this is slow cooling again. This is not quenching it in oil or something like that. This is putting it in the furnace and allowing it to slow cool. Sometimes if you let it air cool, this same reaction will occur, but it depends on the type of steel. There are some steels that become hard just by cooling them in air. And that's one of the things that you're going to talk about in your paper. Okay, so here we have a plain carbon steel, because you see that the iron carbon phase diagram is only two-dimensional, so it's a plain carbon steel. Okay, we don't have chromium or anything else in it. We heat up to 1800 degrees, which is way too hot. You just have to heat up above this A3 line here. Why do they come up with these different lines? And you got to call them something, okay? So this is called the upper critical temperature. This line here is called the upper critical temperature. This line down here is called the lower critical temperature, but they're also known as the A3 and A1 line. There is an actual A2 line, which is somewhere in between here, that represents when it becomes non-magnetic, okay? It doesn't really have much to do with the actual, it's just the transition between magnetic and non-magnetic. So, okay, so what's happening here is if we heat this steel, which looks like it's about, let's say, call it 0.2% carbon, we heat it to 1800 degrees, which is above where I would, but then you really slow cool it. At this point right here, austenite, this is a solid, by the way. We're not making liquid. This is a solid. It looks like this under the microscope if it didn't melt the microscope. So what do we have going on there? Remember the crystal structure. It's face center cubic. So there's room for carbon atoms. So all the carbon dissolves. This is what you're looking for when you put your screwdriver blade in the furnace and let it sit there for 20, 30 minutes or whatever, okay? What happens is all the carbon that was stuck in perlite or some other shape dissolves back into solution, okay? Now, if we get to point B, what happens is it forms ferrite first, okay? So it's kind of like the candy thing, but it's doing it the opposite way. And just bear with me for a second. So what it's doing is it says, hey, I'm going to form ferrite first. You carbon atoms will no longer fit, and it kicks it out. So what it ends up doing actually, in reality, is this area here becomes higher in concentration of carbon. Now, nominally, it's at 2.2%. But as it starts kicking the carbon atoms out, okay, into this area over here, then you have a higher concentration of carbon in this area over here. So at point B, you are starting to form ferrite on the grain boundaries usually. That's where they nucleate. Remember, this is a 2D slice through a 3D structure. So these things are kind of like soccer balls. So think about a bunch of soccer balls all pressed together so tight that they're touching each other everywhere. You deflate them slightly, okay? And then on the surface of these, this is what's happening. So as we go to point C, we've formed as much ferrite as we can, and the concentration of carbon in these little areas over here has reached 0.8% magically. So really what's going on is the composition of this region right here is at this low point here, okay? Then what happens when I go like 1 degree below this, well, or a couple degrees below it, let's say, this thing changes over to perlite over here, okay? So what happened? We increased the concentration of carbon by forming something without carbon in it and just forcing all the carbon into an area that can accept it, okay? Then when it gets to 0.8%, we end up being at the same temperature that it goes through this transformation, and we have perlite. So that's why we have a microstructure that has ferrite a lot of places and just a little bit of perlite here and there, okay? It's kind of like my analogy with the candy, but a little bit opposite. Okay. Now, if I have right at a 0.8% carbon, it's going to cool down and it's going to form 100% perlite. We know that, right? When I have more than 0.8% carbon, what's going to happen? Well, extra carbon is available. More than 0.8, right? So what happens is it has to get rid of carbon somehow to get down to 0.8% because it wants to be at 0.8%, okay? So if we don't have enough, it concentrates it to make 0.8. If we have too much, it has to offload it in order to get down to 0.8 because that's where it wants to be. The problem is that this is not a good structure because the soccer balls that are all pressed together start to form cementite on the grain boundaries, okay? And my analogy for this is think if you took M&Ms and you got them slightly wet, okay? Then you put them together and you dry them out and they form this like peanut brittle, right? Now, the chocolate inside, this is not the peanut ones, okay? This is regular M&Ms. The chocolate inside, especially if it was warm, that would be soft, right? Those candy shells, though, are darn near impossible. If you take a knife to that, what's going to happen? It's just going to be brittle. It's going to be hard to cut. It's going to be terrible, okay? But if I took all those candy shells and dissolved them and make little spheroids out of them, and I put those into the chocolate, could I take that knife and just kind of like cut through the chocolate easily? And those little blobs of candy shell would kind of like flow around the knife edge. I could cut the chocolate, okay? That analogy applies to high carbon steels and how you can machine them. If you just let them slow cool, it's terrible. If you go through a special heat treatment to spheridize the carbides, then that is a condition where you can machine these things. Holy okay. I think that was a mistake, but we'll see. Henry did some 3D printing of some stuff for the casting class tonight. Okay. So here we have a 1% carbon. We heat it to point A. Everything dissolved. It's just the same as the other one. Remember, because you can go up to, in some cases, you can go up to 2% carbon dissolved. Remember that atoms are in an arrangement that they can actually accept carbon. So it looks like this under the microscope. As we start cooling down to point B, remember our goal is to get down to this 0.8, right? So on the grain boundaries, instead of ferrite forming, we get iron carbide, which is that brittle. Iron carbide is really hard. If you ever heard of the word carbide before, carbide bits, carbide grinding wheels, all kinds of stuff is carbide. That has to do with like, actually, it's one of the hardest things there is, okay? So if we have those soccer balls in 3D all surrounded, it's like those M&Ms I was talking about, right? With a hard candy shell, it's hard to cut. So this is what the structure would look like, but hopefully you don't ever produce this because if you do produce this, even though it's kind of soft, if you take a hardness on it, the hardness tester, it's kind of soft. You put it in a machine tool to try to cut it, it doesn't cut very well. It'll dull your tools pretty quickly. So this one, why is this happening? is because in order to get down to 0.8%, we have to dump off a bunch of carbon. It forms iron carbide, grabs some iron atoms, Fe3C, and makes extra carbide on the grain boundaries. How would I make it spheroidized like I talked about with the M&Ms? What I would do is I would hold it at point D for a really, 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 really long time. Okay. And what happens is all these plates and all this chunks of carbide form little spheroids. But I'm talking like 10 hours, something like that at the temperature. Okay. So when you guys got your screwdriver blank, it was in that spheroidized annealed condition so that you could cut it and with your you could cut it with a die, or you could file it, all those things that you did. Remember, it got so hard afterwards that a file wouldn't even touch it, right? So there's some metallurgical magic going on there. Okay, so you understand what's happening here, guys, is we go from austenite to austenite and carbide, and then we go from austenite and carbide. All of the austenite changes over to perlite because it ends up having a 0.8% carbon content. And then it has an average carbon content of 0.8% here because why? Alpha iron can't hold carbon, so it also has to kick it out. So it's really two sets of kicking out carbon. One, well, it's up here in austenite to get rid of some of it, or the austenite plus carbide region, which is over here. And then as it goes from point C to point D, it has to get rid of the rest of the carbon because everything's got to convert over to alpha iron. And now we have that structure. Okay. Again, this is what it would look like under the microscope. Here's the carbides on the grain boundaries. This is a 2D slice through a 3D structure, remember? So, but they look more or less like hexagonal-ish. Okay. That's because when you put spheroids like ish type shapes together, they tend to form these hexagonal. Hey, has anyone ever been to the Devil's Tower? Anyone ever seen that? Well, go look at a picture of it. Those columns of basalt, they're pretty big actually. They're like 3 or 4 foot across. Those are hexagonal. And the reason why they're hexagonal, they got to solidify over thousands of years or something. And they got to go into the shape they wanted to be, which is hexagonal. So pretty cool. Except the heat, I don't know, it's a long story. You can watch something on YouTube, I'm sure, that tells you all how that formed. It'd be very interesting. Same stuff that's going on in metallurgy though. Okay, so let's review some of the terms that we learned. The A1 is the lower temperature at which transformation occurs. A2 is somewhere in between, and A3 is that upper diagonal line, the upper critical temperature, okay? ACM, let's go back and look here. The ACM is this line over here. That's when you're above 0.8%. That's cementite. It stands for cementite. And then the A1 and 3 line come together, and they become the A31 line or A13 line, okay? Eutectoid happens at 0.8%. Hypoeutectoid means below it, 0.8%. Hypereutectoid means above 0.8%. Okay, so I'm going to stop for a second here, the recording. Okay, so if we non-equilibrium cool something, and that has a lot of definitions, like if I'm using the steel that you guys use for your screwdriver and I air cooled that would probably harden significantly with air cooling. Not as hard as oil cooling, but relatively good with air cooling also. Certain steels, if I were to air cool it, they'll become fully hardened, even if they're in real thick sections. Remember that if I have a 2-inch thick piece of steel or something like that, and I pull it out of the furnace, it's going to cool a lot slower than like a little screwdriver blade or something. Okay. So, what happens is if we cool quickly, carbon is trying to get kicked out. Remember we just talked about that? It kicks the carbon out, but that takes some time because the carbon has to migrate between atoms, and that happens kind of slowly. So what can happen is if we cool it really quickly, it wants to go to body center cubic, but there's carbon atoms that did not vacate. They didn't get the eviction notice. Okay. So what happens is that carbon gets stuck in a crystal structure that it doesn't allow it. It's not supposed to be there. So what happens is the other atoms are trying to change into that shape and they can't because there's a carbon atom sticking in the wrong spot there. So what it does is it takes that crystal structure and elongates it in at least one direction. Okay. So one thing I haven't told you yet is that the reason why metals are ductile is because when you have a whole bunch of atoms in a crystal lined up in nice uniform rows, when I say rows, I mean like they're planes really, right? Well, what if I take one plane here and I push in this direction, and I take this plane over here and I push in that direction? What actually can happen is those atoms are like, oh man, I can't handle it. They slide over. And because they have their atomic bonding is such that they share electrons, it can do that. It can just go, yep, I'm okay over here. And what happened is that part actually deformed. It actually got, let's say parallelogrammed a little bit, right? This row of atoms slides over that row of atoms, okay? That's called glide or slip. So most metals, the way they deform ductily is the slippage of these atoms over top of each other. So you can imagine these planes of atoms. If you push hard on this, like set of pool balls that are stacked on top of this set of pool balls, eventually you can get the pool balls to jump over one set of balls, right? Okay, that's called slip. When the surface is not nice and flat, though, it makes it a lot harder. If I had like different size pool balls in there, well, now it's just not this nice plane, and one ball has to kind of go up and over one of them. So it's kind of like dragging something over a smooth surface or dragging something over rough terrain. Okay. So the carbon doesn't really have time to combine to form cementite. So what happens? It gets stuck there. It makes the body center cubic crystal stretched out, and now it becomes brittle because it prevents that slippage from occurring, which prevents ductility, right? So it stresses the structure out. The structure is called body-centered tetragonal. And the only difference between body-centered cubic and body-centered tetragonal is that one of the sides is unequal. You see that? It's body-centered cubic, but stressed out. And this structure is called martensite because there was a metallurgist called Martin at one time. I think it was a German metallurgist, and developed some of this stuff. And so they called that martensite. That's the really hard stuff. Now, we typically don't want to have martensite as our end result. In fact, remember I said that if you take and you quench your screwdriver and you drop it on the floor, it's likely that a screwdriver is going to fracture just by the falling of it. For sure, if you hit it with a hammer or something, it's going to go dink, and it won't take almost no force to do that. Why? Because it's under a lot of residual stress, because this is like changing the volume of the part, actually. Okay. And it's very hard. So, there's no ductility. Okay. So what's going on is the slip planes, these glide planes where the atoms used to be able to slide over each other, they're all messed up. So if you remember that will give you, as far as mechanical properties are concerned, it'll tell you a lot. Now, under the microscope, it looks like you put your face about a foot away from a bale of hay. That's what it looks like under the microscope. It looks like these little feathers almost, like going in all random directions. Okay. And it's just showing you that whole structure is messed up. You can't even see the grain boundaries or anything because it's so messed up. Okay. The maximum hardness you can get is Rockwell 65 to 67. Okay. So a normal maximum you'd see is Rockwell 64, somewhere in there, something like that, if you had enough carbon. So the deal is, the more carbon you have, the harder it can get. Hence your experiment that you're doing, right? Your goal is to back calculate the carbon content. So we're going to take hardness and back calculate carbon content knowing certain things, okay? So, okay. Wow, that is lecture number 1.